Hello everyone, it's my pleasure to give this presentation here. I'm Shaoxuan Wu from Beijing Institute of Technology. Today I will introduce a new concept named cognitive thread. It supports system of systems for complex system development. I will introduce from the following 5 parts: introduction, related works, cognitive thread, case study, and conclusion. In recent years, model-based system engineering is considered as a possible solution for complex system development. The model-based system engineering uses models to formulate systems, like system architecture, dynamic system architecture, power system architecture, software architecture, control system architecture, and research and development process and activity. Systems that gathering all these elements to design complex systems by model-based system engineering can be seen as a typical system of systems. However, there still exist some problems, like how to integrate heterogeneous models and data in a system of systems, how to identify the cross-domain dependency between models, how to combine models with development activities. So, the concept of digital thread is proposed to solving these problems. The digital thread can link digital models for management process like traceability management and change management. However, it still lacks the ability for understanding the scenario information like process and life cycle. Therefore, it also lacks the ability for making better decisions based on this information. For this reason, we believe it is very necessary to enrich the current concept of digital thread by adding the cognition ability for models, process, organization, and things in the system of systems. Besides, we also believe that corresponding methods or tools for realizing the concept are also needed to improve the research and development efficiency of complex systems. So, in this paper, we propose a new concept named cognitive thread to support system of systems for developing complex systems. And we also propose a cognitive thread construction approach based on OSLC specification and knowledge graphs. Besides, a tool chain is developed for traceability management based on our approach. The concept of digital thread has been successfully applied in the design of complex systems like F-22 fighters for linking digital models of the system of systems. Many open standards like open services for lifecycle cooperation and function mockup interfaces have emerged to support data integration and interoperation. Knowledge graphs is widely used for linking models and data. So we believe it is an opportunity to combine all these concepts and technology we mentioned above. Let's begin with the cognition model in psychology domain. Nielsen believes that the process of cognition will be divided into 3 parts, which are individual behaviors, cognition, and metacognition. And they have the interaction with each other. We introduced this concept into engineering domain to analyze the scenarios and system behaviors in system of system. And we also refine the cognition into 3 parts: the recognition, cognition information, and realization. This slide shows our concept of cognitive thread. The cognitive thread is a technical concept frame to identify the interrelationship of data, information, and knowledge in the system of system, as well as the process of understanding and analyzing this interrelationship for supporting research and development activities. Our concept of cognitive thread enrich the current concept of digital thread by adding the cognition process and the ontology for interrelationship between scenario systems and models. And this slide shows the formalized expression of cognitive thread. We consider the system composition and the interrelationship between scenario systems and models. We also consider the interaction in the system of system, like the data and the operation. Besides, we also consider the cognition elements like the at metacognition and the cognition process like the scenarios and the realization. This slide shows the construction approach for cognitive thread. In step 1, we transform the data and model into OSLC services by mapping the data structure to OSLC core model, and then we generate OSLC services. These OSL services are represented by RDF, that is Research Description Framework. In this RDF, there are all the information about the data, including the URI, Unified Resources Identifier. It can be used to find the OSLC services. In step 2, all the OSLC services and scenario will be captured. And then the ontology of cognitive thread will be established and represented by the knowledge graphs. And then, based on the reasoning pattern, we can doing the knowledge graph-based reasoning. We use the case study of advanced driving assistance system designed for verify our approach. And because the life cycle of ADAS is relatively long, the traceability management of models and data is needed in the early lifecycle phases. We adopt the toolchain of Excel, Metagraph, Simulink, and CAD tools for requirement analysis, system architecture design, system simulation, and CAD modeling. And these models and data will be transformed into OSLC services by data link. It is a tool for developing OSLC adapter. By generating OSLC services, users can operate these models and data by standardized URL in this figure. And we also developed a platform named OSLC Service Manager. In this platform, traceability of models are established manually. And this slide shows the process of traceability management. The question of simulation engineer, like I want to know all the relevant components of OUT1 in Simulink model VDP, will be represented by the URL and be further transformed into query rules of knowledge graphs. The query rule is based on cyber language. To improve the efficiency, we developed an OSLC service plugin for Simulink. The engineer can get the architecture model components in the plugin, which is the result of his question. Here is the video of our case study. These are the table for requirement analysis in Excel. And this is the OSLC adapter for Excel. And in this page, you can find all the requirement contents in Excel table. The Metagraph is a tool for architecture design. You can establish a model based on system modeling language. And this is the requirement diagram. This is the ID of the requirement diagram. And in OSLC adapter for Metagraph, you can find the model information of the requirement diagram. And we also build a Simulink model, and in this adapter, you can find the model topological information. We also use Pro-E for detailed design of CAD models. And in CAD adapter, you can get geometric information of CAD models. This platform is the OSLC Service Manager. You can find all the status information in the homepage. And in Service Management module, you can get all the OSLC services we generated. For example, you can find specific requirements. Besides, it also can be used for find the information of simulating model and architecture model and city models. In traceability management module, the engineering can establish the links of OSLC services manually. For example, you will establish the links of requirements and the object of architecture model and the Simulink block. In this page, you can establish the link of these OSLC services manually. And we will represent this interrelationship as a knowledge graph. You can find the newly established links of OSLC services. And we can doing some reasoning based on question templates in this page. For example, you can find the relevant components with the MU. And the engineer can get the traceability information by clicking the Unified Resources Identifier. And to improve the efficiency, we also develop an OSLC plugin in MATLAB. For example, if a simulation engineer wants to know whether the simulation result is fit the requirements, he can open the traceability plugin in MATLAB. All the blocks in current open model will be listed in the plugin, and he can get the relevant OSLC services. And based on this information, he can make better decision in his design process. Compared with other traceability approach, our method has the following advantage. First is OSLC provides a more flexible integration in the life cycle range, and second, knowledge graph provides a better understanding of data traceability for stakeholders in the system of system. And last, the toolchain and plugins provides a better efficiency in the research and development process. Of course, there still exists some limitation of our works. First, our concept of cognitive thread is not applicable to all the system of system. In this paper, we only focus on the system for complex system development. Second, The correctness and completeness of cognitive threat formalism are under validating. In addition, different approaches of developing OSOC adapters bring us about different granularity of cognitive threat, which means that the measurements of the return on investment of building cognitive threat are needed. And in conclusion, we propose a new concept named cognitive threat and its construction approach to support system of systems for developing complex systems. In the future, we hope to mature the concept of cognitive threat and combine this concept with AI technology to realize the intelligent-based cognition in the system of systems. Thank you.